Hello, so today we will look at the case where we have equal roots. So we will look at the case of double characteristic value. So when we calculate the eigenvalues are going to be equal. So let us consider the matrix A. So let lambda 1, lambda 2 be the characteristic values. Of the coefficient matrix A. Of the differential equation x dash equal to ax, and let lambda 1 equal to lambda 2 equal to lambda, and let us take alpha to be the corresponding eigenvector. So let alpha be the corresponding eigenvector. And here, okay, then alpha e raised to lambda t is a solution, and here A is such that as we have seen in the other method. Okay, so here the coefficient matrix A is such that, so A11 equal to such that A11 such that it does not satisfy the condition. So A11 equal to A22 not equal to 0, and A12 equal to A21 equal to 0. So if the matrix is of this form, then there is only one solution. So we are looking for a system which has two solutions. Now let us look for the second solution. Now the second solution is of the form that will be of the form x equal to, so we have taken it in the form gamma t plus beta e raised to lambda t. So this is the form of second solution. So we need to find out gamma and beta for the second solution. So here we need to find out gamma and beta so that it is a solution. Now we have the equation x dash equal to ax, okay, that is dx by dt equal to ax. Now x is a solution of this equation, so therefore it satisfies. So since it is a solution, it satisfies the differential equation. So that implies, so you will get gamma t plus beta. So let us differentiate x. So gamma t plus beta into lambda e raised to lambda t plus gamma e raised to lambda t, that will be equal to a gamma t plus beta e raised to lambda t. Now let us divide throughout by e raised to lambda t on both sides. So we will have gamma t plus beta into lambda plus gamma equal to a gamma t plus a beta. Okay, so now let us collect the coefficients of a. So therefore a gamma minus gamma t will be equal to, okay, a gamma minus gamma t plus you will have a beta minus beta lambda minus gamma equal to 0. Now this holds for every, so this is a gamma t. Now this holds for every t, so that implies, so this holds for all t if and only if. So a gamma minus, here there is a lambda over here, okay, lambda gamma must be equal to 0, and you must have a beta minus lambda beta minus gamma, that must be equal to 0. And now the first equation, so you have, so that implies a lambda, okay, a gamma must be, so a gamma must be equal to lambda gamma, so that is the first equation, a gamma minus lambda gamma must be equal to 0. So which is of the form so it is of the form ax equal to lambda x. So this implies gamma is the eigenvector of A. So gamma is the eigenvector of A. So therefore here gamma must be equal to alpha. So alpha is the eigenvector we have taken corresponding to the eigenvalue lambda. So here the vector gamma must be the eigenvector lambda. So now this gives, so let us now rewrite the first equation. So you will get a beta minus lambda beta, so a beta minus lambda beta, that will be equal to alpha. So if you take beta outside, you will get a minus lambda I beta equal to alpha. So here we need to solve this equation for obtaining the value of beta. Okay, so solving this equation, so we obtain the value of beta. So hence you will get your two solutions. So therefore the two solutions are, So that will be alpha e raised to lambda t. So this is the eigenvalue and the corresponding eigenvector, and the next one is alpha t plus beta e raised to lambda t. So these will be the solutions of your equation. And okay, let us state it as a theorem. So consider the homogeneous linear system. dx1 by dt equal to a11 x1 plus a12 x2, and dx2 by dt equal to a21 x1 plus a22 x2, or that is dx by dt equal to ax, where a is equal to a11 a12 a21 a22, and x is equal to x1 x2. So where a11 a12 a21 and a22 are real constants, so which are not such that so you have a11 equal to a22 not equal to 0, and a12 equal to a21 equal to 0. So they will not satisfy these conditions. Now suppose the two characteristic values lambda 1 and lambda 2 of A are real and equal, and let lambda be the common value. And let alpha be the corresponding eigenvector of A, and beta be a vector such that vector satisfying the equation. So A minus lambda I beta is equal to alpha. Then on every real interval the vector functions defined by alpha e raised to lambda t and alpha t plus beta e raised to lambda t form a linearly independent set of solutions of the equation x dash equal to ax and x is equal to c1 alpha e raised to lambda t plus c2 alpha t plus beta e raised to lambda t, where c1 and c2 are arbitrary constants. So this is going to be the general solution. So it's a general solution of the differential equation. So this is the case when you have real and equal roots.